Namaste and welcome to yet another lecture on mathematical foundations for machine learning. We have been looking at probability and topics in probability now, and in the last class we looked at the idea of conditional probability. We said that okay, occurrence of one event, does it give any update about or does it give any information about another event? And on that note we figured out that okay, there are two pairs of events wherein which occurrence of one gives no update about the other and occurrence of one gives a complete update about the other, these two being the extremes of I mean on the extremes. We were looking at can we get partial information about event A occurring event A upon the occurrence of event B or vice versa. So, we basically looked at that, and that is where we got into the notion of conditional probability. We also talked about the interpretation of mutually exclusive events, and we also got into the idea of independent events, and we said that look, if the posterior probability is equal to the prior probability, or if posterior probability of A given B is equal to the prior probability of A, then you said that the events A and B are independent, and we said that P of A intersection B is equal to P of A into P of B in case of independent events, and in case of mutually exclusive events these two events cannot occur together, and therefore the intersection is an empty set, and therefore the intersection probability is also 0. This is something which we had. Now we are going to take another step into this. So the question that we are going to ask here is, suppose I have multiple causes for a particular effect, what is the probability of this effect actually occurring, right? It could be a simple example like what I told you in the previous class, where we had okay, I have an event of me going late to the workplace. Assume that I make an exhaustive list of the causes for me to go late to my workplace, which could be a problem with the traffic, or it could be some personal issue with me. It could be a simple thing like me having gotten up late, or let us say it could be a problem with my vehicle. Assume that we are just these are the only three causes which could be the reason for me going late, and it is also like okay, it is not that I get up late and therefore I get stuck in traffic and therefore I go late. No, I do not put it that. If I say that okay, if I get up late, that is the only reason for me going late to the office going late to the office or the workplace. If there is a traffic, that is the only reason for me to go late to the workplace, or if there is a problem with the vehicle, that is the only reason for me to go late to the workplace. I mean it cannot be a combination. So that is what I am trying to tell you now. Now if this being the case, now I want to estimate the probability of me going late. How do we get that? Okay, so let us look at this. Assume that I have my sample space omega, and I have let us say the event A1, event A2 and event A3 I have, where A1 is the event of let us say waking up late, event A2 let us say event of traffic delay, A3 event of problem with the vehicle, I am going to define event B, which is the event of reaching late to the workplace. So, where am I going to draw? I am going to say this is event B, this is event B, right. So, I could go late because of a problem with the vehicle, or I could go late because I had a problem of traffic delay, or I could go late because I got up late. Now, the question that I ask is, what is for P of B? What is P of B? For that I must know what is this event B, how is it related to this A1, A2, A3 and so on. So, what is this event B? If you look at event B is nothing but B intersection A1 then union B intersection A2 union B intersection A3, right. B intersection A3, this is what I have. Now, if you look at A1, A2, A3, these three fellows are basically disjoint. So, what we see here, we see that A1, I will write this A1 or AI intersection AJ is equal to empty set for I is equal to 1, 2, 3, right. You take a specific j, which is j is also in 1, 2, 3. Suppose if I take I say that whenever I is not equal to j. So, let me write this whenever I is not equal to j. And what I say is, we also see this, if you take the union of A1, A2 and A3, you end up getting your sample space. So, let me write this union of I is equal to 1, 2, 3 AI is basically my sample space, right. Therefore, what I have is B is equal to B intersection A1 union B intersection A2 union B intersection A3. Therefore, now if I look at probability of B is nothing but probability of B intersection A1 union B intersection A2 union B intersection A3. Now, since A1, A2, A3 are disjoint, we have P of B is equal to P of B intersection A1 plus P of B intersection A2 plus P of B intersection A3. This is what we have, right. This is by the third axiom, the probability that we had, which says that if the events are disjoint, then the probability of the union is equal to the sum of the probabilities. This is by the axiom 3 of our probability axioms. So, we have this. Now, what does it say? Let me rewrite this. We have P of B is equal to P of B intersection A1 plus P of B intersection A2 plus P of B intersection A3, right. I have this. Now what do I get here? What is this actually? P of B intersection A1. If you look at the previous slide, we had A1 to be the event of waking up late. So what am I asking? This probability is basically the probability of me waking up late and going late to the office or to the workplace, and this is nothing but the probability of me getting stuck in a traffic jam and then going late to the workplace, and this is the probability of my vehicle having a problem and then me going late to the workplace, right. That is what we have. Now what you see, we can write this as probability of B given A1 into P of A1 plus probability of B given A2 into P of A2 plus probability of B given A3 into probability of A3, right. This is what we have. Now what is so great about it? If you look at this, these were talking about the reasons for me to go late to my workplace, which is me waking up late and then going late, me getting caught in traffic and then going late, my vehicle having a problem and me going late. That is exactly what we are there, what we are looking for. Whereas if you look at this expression that we have written here, it is the same thing, but we have written in terms of conditional probability, and what does this tell me? This is interesting. It says the probability of me going late given that I got up late, and what is the probability that I would get up late. This is the probability of me going late given that I got caught in a traffic jam. What is the probability that there was a traffic jam of getting a traffic jam. This is probability of me going late given that the vehicle had a problem, and what is the probability that the vehicle will have a problem. That means we have captured that the probability of going late in terms of the conditional probability of the event of going late with respect to each of those causes. We have captured in terms of each of those causes being responsible for going late, and what is the probability of each cause being there, right. That is what we have had here. So what we have, we will generalize this, and then we will come to very interesting understanding here. So what do we say? We are going to look at this. Suppose, so before that let us write a compact form of this. It says P of B is equal to sigma I is equal to 1 to 3 P of B given AI into P of AI. Okay. So how do we generalize this? Can we generalize this at all, and how, if yes, how do we generalize this? Of course we can generalize this. Let us look at how this happens. So I am going to make a few assumptions here, or I am going to say that look, these conditions must be met for me to generalize this. So what I am going to do is I am going to write this. Suppose omega is a sample space and A1, A2 etc. An are partitions of omega. Now what do we mean by partition? I hope we remember the definition of partition. We said that look, A1, A2, An are mutually exclusive and collectively exhaustive. That means there cannot be any more reason for a particular effect. So what we say is like you have an exhaustive list of possible reasons, you have an exhaustive list of all the events which could actually be which are basically mutually exclusive. So, what happens, these events are mutually exclusive and collectively exhaustive. Collectively exhaustive means you take them, the union of all these events, you get the sample space, and that is facilitated by the fact that they are also mutually exclusive, right. So, we had this are partitions of omega, and B is any other event, of A of omega, then P of B is given by let us first draw the Venn diagram and try to understand this, and then we will put the expression for the same. So, what do we have? We have this. So, I have my sample space omega here, I have let us say A1, I have A2, I have A3, and let me just say okay dot 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 I have A n, right. We have this, and I am going to do this event B. This is event B. I mean, another easy way to understand is like, suppose you have a multi-layered cake and then I give you a cylinder, a hollow cylinder, you pierce it into this multi-layered cake, and then I want to find out what is the amount of cake that has got into this empty cylinder, right. It passes through all the layers, and then I want to find out what is the amount of cake that is there in the hollow cylinder that I have. That is exactly what I am doing here. So, I am going to say probability of B is equal to probability of B given A1 into probability of A1 plus probability of B given A2 into probability of A2 plus etcetera plus probability of A n B given A n into P of A n. Compactly written, this is going to be this way. I am going to write it as P of B is equal to sigma I is equal to 1 to n P of B given A I into P of A I, and this is what we call as the law of total probability or total probability theorem. This is basically the law of total probability, or what we call as total probability theorem, right. Okay. Now, where do we go from here? In fact, we will even look at a simpler case where we do not have this multiple multiple causes or whatever, multiple events. We just have an event A, and then I am looking at event B. In that case, what I am going to do is just look at let omega be a sample space with two events A and B. With events A and B. Now, I want to do the same business that I did. I want to look at P of B. I want to look at P of B, but I want to I want to make a partition of omega with respect to A, or using the event A I want to make a partition, and then I want to look at what is the probability of B, right. Can I make a partition with just one event A on the sample space? what does it mean? So, suppose I have this omega and I have an event A, right. Can I make a partition of the sample space using A? Of course, it is possible. A and A complement make a partition of are partitions of omega, are partitions of omega, because we know that A union A complement is omega and A intersection A complement is empty set, partitions of omega. Therefore, I can write P of B is equal to P of B given A into P of A plus P of B given A complement into P of A complement, right. That also is, I mean, that is exactly how this total probability theorem would look like if just I am going to have one have A and A complement to be the partitions, right. Okay, great. In all the cases, in the idea of, let us say, our total probability theorem, we said that event B, when we considered that example of me going to my workplace late, we said that look, event B is the event of me going late to my workplace, and there were multiple reasons for me to go late to my workplace, which were basically because of something personal, like I got up late, or it could be because of traffic jam, or it could be because of a problem with the vehicle, or it could be any other reason. We will put all possible other reasons for me to go late, put it into that block called any other reason, let us put it that way. Now the question that I ask is not the probability of me going late, but I ask this: suppose I go late on a particular day, right. I go late on a particular day, I ask this question: what is the probability that it was because of traffic jam that I got late? What is the probability of what is the probability that I have gone late given that I got up late? Or I could ask this question: what is the probability that I have gone late, given that I have gone late, what is the probability that it was because of a problem with my vehicle? I hope the question that I am asking is pretty clear to all of you. In the previous case, we were trying to nail the probability of that effect based on these causes. Now the question that I ask is, look, I know that this effect has happened, I know that I have gone late. There is somebody who is asking, so the probability of, I mean, I have seen that it is observed that I have gone late. So now what we want to figure out is, what is the probability that having gone late, what is the probability that it was because of traffic jam? We are basically asking the other way around, which means we are going from P of A given B to P of B given A. Is that clear? We are talking about the reverse of the problem. That means I know the effect is there, I want to find out the probability of this effect being caused because of each of those fellows, each of those causes that I have, right. So what am I going to ask for? I am going to ask for P of AI given B. In the previous cases, in the total probability theorem, if you looked at, we basically wrote P of B is equal to P of B given AI into P of AI. This is what we had, and then we did a summation here, I is equal to 1 to n. This is what we had. Now I am asking us, I am not interested about this P of B, I am not interested about the probability of me getting late to the workplace. Instead, I am going to ask this question: what is the probability of, let us say, A2 being the cause for me having gone late? I hope you can see the difference between the two things that I have marked here. This is saying, given that I got stuck in traffic jam, what is the probability that I got late? Now given that I was late, what is the probability that it was because of traffic jam? That is the question. It is the reverse question that we are trying to answer, it is the reverse one that we are asking. How do I get this? it is observed that I have gone late. So, I want to find out the posterior probability of traffic jam being the cause for me going late, having observed that I have gone late. That is the question that we are asking. So, can we do this? Oh, that is pretty simple. There is no problem here at all, because I know how to get the conditional probability. I know that P of A2 given B is nothing but P of A2 intersection B divided by P of B. That is pretty simple and straightforward, right. Okay, let us write it again. P of A2 given B is equal to P of A2 intersection B divided by P of B. This is what we have, right. Now, but what is P of A2 intersection B? P of A2 intersection B is nothing but the probability of me going late given that A2 was the cause, given that the event that given that the traffic jam has already occurred, or given that I have got up late, whatever that A2 that cause was, into probability of A2 divided by P of B, right. This is something which we know. I just rewrote this intersection probability in terms of the posterior probability of me going late given that the event of traffic jam has occurred, into the prior probability, into the probability of traffic jam occurring. That is the thing that we have. So, what do I have here? I have P of A2 given B is equal to P of B given A2 into P of A2 divided by, what is P of B? That is something which we got from our total probability theorem, which says, look, this is nothing but I is equal to 1 to n P of B given AI into P of AI, right. This is what we have, and that is precisely what is Bayes' theorem. And that is what Bayes' theorem is. What it says? It says Bayes' theorem is P of A2 given B. I will, instead of writing it as A2 given B, let me write this as P of AK given B, some kth cause being responsible for you going late. So, I want to find out the posterior probability of kth cause being responsible for me going late. This is given by P of B given AK into P of AK divided by sigma I is equal to 1 to n P of B given AI into P of AI. This is the Bayes' theorem that we have, right. Okay. So, let us just rewrite this Bayes' theorem. Let us make the proper statement here. Given A1, A2, etc. An partitions of omega and B be any other event on omega of omega, we have, let me do some small color coding here, we have P of A k given B is equal to P of B given A k into P of A k divided by sigma I is equal to 1 to n P of B given A I into P of A I. This is my Bayes theorem, right. This is my Bayes theorem, which says that look, the posterior probability of a cause being responsible for the effect is related to the prior through this expression that we have. But I want to understand this further. It says A k given B, B given A k, P of A k, okay, the point is like, yeah, these are all like, you know, there. But can I get a better meaning for this? Can I get a better interpretation of this? That is what I am trying to look at now, right. I want to look at a better interpretation for like whatever that we have written here as Bayes theorem. Now let us pay closer attention to each of those terms involved in Bayes theorem. There are at least 4 terms that you could see which are involved in Bayes theorem, namely this one, which is P of A k given B, then we have this one P of B given A k, then there is a P of A k, and the denominator is basically my probability of B, is what I have, right. Can I interpret it differently? Now look at the term P of A k given B and the term P of A k. This is the conditional probability. P of A k given B is the conditional probability, and I am going to call this as the conditional probability is always called as your posterior probability, this is posterior. And P of A k, this is the unconditional probability. So, this is basically my prior probability, right. And whatever is there in the denominator, which is nothing but P of B, which is equal to sigma I is equal to 1 to n P of B given A I into P of A I. This is basically the effect that I have. B is basically the effect. Suppose I have multiple causes, then this guy is going to be the effect, or this is the evidence that I have, right. This is the evidence that I have. So, I will write this as my evidence. There is one more guy which is who is left over here, which is nothing but my probability of B given A k. What is probability of B given A k? This is the probability of the likelihood of me going late given that the A k event A k has occurred, right. This is basically my likelihood of event B occurring given that event A k has occurred. This is what we have. So, probability of B given A k is the likelihood of going late given that the event A k has occurred. So, let us put all these things properly in a readable format and try to understand Bayes theorem clearly. So, what do I have? Let me again write the expression for Bayes theorem. P of A k given B, this k is basically subscript, A k given B is equal to, we had P of B given A k into P of A k, the whole thing divided by, we had P of B which is equal to, I will put this as P of B and because P of B again I will write it separately, P of B is nothing but sigma P of B given A I into P of A I. Now we had got the meaning for each of those terms, so I am going to put everything together in terms of its meaning. So I will use the same color code that I have done here. I will use this is basically posterior is equal to likelihood divided by evidence into prior. This is my interpretation for Bayes theorem. The posterior is equal to the likelihood by evidence into prior, and this is precisely what we will use. In fact, if you have multi-class classification to be done, something similar that is what you will use, but then of course we will look at the distribution. Therefore, we will have to talk in terms of the random variables and stuff. So we will be doing that. So now what we have seen is in the last 4 lectures we have actually looked at the ideas of probability, we have looked at the idea of events and so on, and then we looked at conditional probability, we looked at the total probability theorem, we looked at Bayes theorem and so on. In the next class what we will do is we will try to look at a couple of problems, we will try to look at a couple of problems or probably try to even look at some more insights into all these probability terms that we have, and then what we will do is we will embark on our journey, another journey wherein which we will look at random variables in detail. So our journey into the probability begins with the understanding of Bayes theorem. We are going to start with the idea of random variables and stuff. We will look at random variables, how do we characterize random variables, what is it that we have here. So we will do a whole lot of stuff, and that will be the focus of the lectures next week. So in the next class what we will do is we will look at maybe getting some more insights about this probability, which is the foundation in terms of maybe the idea of event space, probability space. Now we have understood all these things clearly, but for us to do all these things certain foundations must be there, and that will be the focus of the next class. When we come back we will look at the idea of event space, we will look at the idea of what is called as a probability space, we will look at the idea of a probability space, which is basically this triplet that you have, which is omega, b and a function p, like how we had in terms of when we did vector space. We said that look, there is a structure that is there where you had the field, over the field you defined your vector space, and then you gave certain operations in the vector space. Similarly what we are going to do is, I should not have said similarly, we will look at, in the case of probability also we need to have something called as a probability space, which will include the sample space and this B, which is basically collection of the subsets, and we will look at this function p, which is going to do something to the elements in this B and fix up a probability. So the focus of this next class would be the idea of probability space, which is very fundamental and which is very essential for us to build on. So we will just have a bird's eye view of this probability space in the next lecture and follow it up with the next week lecture on random variables and so on. Namaste.